Hey there, and welcome to this next lesson on high level mathematics. So we're moving on to a whole new area now, topic, which is statistics. So very different to what we've done so far. Um, Statistics is almost seen as some like kind of some like sub category of mathematics, um, which is all about study of data and trying to extract useful information from that data and how to represent it with graphs and things to get an idea of what's going on with the thing that we're studying. So we're going to be looking at first, which is just data collection and analysis. What are different types of data? How do we collect it? How do we analyze it? So we're going to look at questionnaires. How do we make a questionnaire to actually get reliable data? Um, we look at what is sampling, when we would use it, why would we use it, what are some limitations of it. We look at bias. What is bias? How does it affect our results, and how can we try and avoid it? Because it's typically a bad thing. Um, then we're going to look at different types of data. Certain things, we might want to be looking at when we're studying a particular thing. Different types of data we might collect. We're going to look at different types of average, which is how we then deal with, numerical data and get like numbers that kind of represent the overall data set. And we're going to look at quartiles as well, which is more about distributions of data. So, where is the data distributed? Is it generally quite low or high or even? Or I'm going to take a look into, how that works. So, first of all, let's look at questionnaires. So, one of the simplest ways, we can collect data, really. So that could be something like this, and maybe we're trying to collect data on how much people exercise, and we have this questionnaire, and this is a typical type of question you might come across, and they'll ask you, what is wrong with this questionnaire? Um, so you might want to pause here and see if you can see yourself, like things that might be wrong that might, influence our results. We're trying to get an objective view of, people's exercise habits. Um, so first thing is a time frame has not been specified. So you say, how much time do you spend exercising? Is this per day, per week, per month? It's ambiguous. You need that needs to be specified. Another one is that options are overlapping, which could be somewhat of an issue. Like, say if someone spends 2 hours a week, do they put 0 to 2 hours, or do they put 2 to 4 hours? Which category do they fit in? So you want to sometimes be more specific on those boundaries. Another problem would be is that it doesn't account for all possible answers. What about someone who's really into their exercise? Maybe they do sports and stuff, and they're doing 7, 8 hours a week. How or whatever, because we don't know what the time frame is. Uh, what would they select? Because we only go up to 4 to 6 hours. So we want to make sure we're accounting for all possible answers to the questionnaire. Here's another one with perhaps some more obvious problems. Again, you might want to pause here and see if you can spot those errors for yourself. Um, so so this one, the problems are kind of just with vagueness. So it hasn't been defined what constitutes a good grade. So you see, how many good grades did you get this year? What is a good grade? To one person, getting a grade 6 might be good, whereas for someone else, they might not be happy with anything less than an 8. Like, so you need to clarify, what does a good grade mean? Second of all is that some of the options are not really specific enough. Like, none is a specific amount, 0, or all of your grades. Now, some people might be doing different numbers of subjects, so that could still be a little bit vague, but all of them means basically 100%. But when you say a few or many, what does that mean? How many is a few? How many is many? Again, it's subjective, and we don't want to be subjective. We want to have very specific answers. So that's what the problems with this one is it's not it's too vague. You need to be specific. So here's some tips on how to write a good questionnaire to collect data. Ensure the questions are clear and leaves no room for interpretation. So there's only one possible way you could be interpreting that question. Avoid using words like good, bad, big, small, which are kind of relative. If I say, is a mouse big? Well, compared to us, no, it's very small. Compared to an ant, a mouse is huge. So you yeah, you don't want to use relative amounts like that. Make sure options are clear with numerical quantities wherever possible. If we're collecting something that is numerical, uh, ensure that each option is distinct and that they don't repeat or overlap. So, yeah, so there's not confusion about which one you would tick. And finally, make sure you count for all possible answers. So, yeah, if you get someone and they don't fit one of those categories, then they might be forced to then put in a category that isn't actually accurate, and it's going to influence your results. So you want to account even for extreme cases. So sometimes you might just have an option at the end that is just other, it just accounts all other options. So say something like this. So I'll give an example of a good questionnaire here. So I said, which store do you spend the most on fruits and vegetables? So, and I've given three options, three shops, and then if maybe they don't go to any of those shops, they can just select other. Uh, and I've been clear with the question, which store do you spend the most? Like if I said, which store do you get the most fruit and veg? Is that in terms of cost? Is that in terms of quantity? And I've made it specific. How much do you spend? And I've said with things like fruits and vegetables, as opposed to how much do you spend on healthy foods? Because again, healthy, that could be subjective. What one person considers healthy might not be what someone else would consider healthy. So you see, I've gone there to be very, very specific and then get very clear options, distinct options, and I've allowed for any other case that might not fit those options as well. So those are the things we have to consider when doing a questionnaire. It's very easy to, make those mistakes. So now we're going to look at sampling and bias. So we've got our questionnaires now. How are we going to go out and actually collect data? Um, So one example would be, say, a census, which is where you collect data from an entire population. So these are some key words. Population is like not necessarily people population. People is just population is just all of the members of the thing that you're studying. So it could be people, it could be animals in the wild, it could be products being produced on an assembly line, it could be all sorts of things. And a census is basically when we test every single one in the population that we're studying. An advantage of this is that we're collecting data for everyone, so it gives just a very accurate picture of the population. But the disadvantage is that that in terms of time and money and energy and resources, it can just be completely impractical sometimes, especially if the population is used up in in the testing process. Like we'll take a look at examples where that happens. What exactly that means. So sampling is typically what we do, where we take some subset of the population and we want to ensure that sample is representative. The advantage of that is quicker, cheaper to collect the data. There's also less data to analyze once you actually get it done, collect all your data. The disadvantage is that it might not represent the overall population because you're not testing the whole population, you're only testing part of it. Uh, Either because it's too small or it could be biased in some way. And we're going to look at bias soon enough, which can influence our results. So we look at different types of sampling. How do we collect a sample then? Random sampling is, the most common and simplest way we do. Well, not simple in execution, but simple in the idea in that you have a population, maybe you assign each member in the population some number, and then you can have some computer just randomly generate some numbers, and then you pick those numbers. Uh, it's great for getting a fair representation of a population because everyone is just equally likely to be picked. Certainly if it's large, but it could be hard to implement if it's large. An example of this would be basically selecting, say, employees from a company by randomly generating employee numbers. Each employee tends to have a number associated with them, and you could just randomly generate some. Systematic sampling is something when we start off from we pick one person at random, like one member, and then we grant in like say the first n, and then we pick every nth member after that. So that's more when you're dealing with something that is like sequential, where there's a sequence, there's like an order to the population. So you say a member is chosen at random from say like the first n number of members, and then after that you select every nth member, and that will create like a sequence of so many members. Um, this is great and easier to implement than random sampling, and selects evenly over an ordered population. So if you want a nice even spread, because if you select randomly, there's a chance you could maybe select more at the beginning or more at the end. If you're doing it systematically like this, you're getting a good even spread. But it can introduce bias if there's patterns in the population. And if you're selecting every 10, but if there's a pattern that kind of repeats every 10 members, then it's going to introduce a bias because you're going to keep selecting those ones that fit the pattern and not the ones that don't fit the pattern. So that's a potential issue. It's often used on things like assembly lines, where a factory is producing things, and you'll select every end product and you take them for testing because you want to ensure that you're getting good, consistent uh, products that are working. And if you have some issue uh, that affects a small batch of products, typically it's not going to affect all the products. It's only going to be that small batch. So you make sure you get a good mix. Um, this is also an example of something where you wouldn't use a census. So, like what I said earlier, where sometimes you're using up the population when you test it. So, say if you a company generating building like I don't know, phones or something, when they then take some to test, they normally test them to destruction. Like they smash them, they'll dunk them in water, and to test like say durability and things like that. And so once you finish testing, the phone is destroyed, and so you can't test every single phone, could you? Because you're just going to destroy them all. So you have to take some sample. So that's an example of where census would just not be possible. Um, Let's look at a stratified sample. So stratified sampling is when we divide the population into subgroups and we sample individually to account for different sizes. So we don't select randomly. We're a bit more selective. Um, we do select randomly, but not completely. So what we do is we divide our population up into various distinct subgroups called strata. And then we take a random sample from each strata relative to the size of the population. So we use this form when we want to ensure that all subgroups of a population are being accurately represented in the sample. But this will require more detailed information about the sample, about the population and their subgroups and how many people are in each subgroup or things, members. Um, so it's a bit more work, but it can be beneficial. A simple example would be, say, if I wanted to sample a dance class, but the dance class is 80% girls and 20% boys, a sample of 20, if we just took 10 and 10 of each, that wouldn't be representative because there's a lot more girls in the group than there are boys. So it makes sense if you take 80% of your sample being girls and 4%, 20% being boys. And so an 80-20 split of 20 people would be 16 girls and 4 boys. So we take away we get the girls aside, get the boys aside, and then randomly select 16 of the girls and 4 of the boys, and then that would be a representative sample, a stratified sample. Um, so this is something that's commonly tested because it's it takes a little bit more um, understanding. So here's some other types of sampling, less commonly tested. Capture and recapture is typically to do with like trying to estimate the numbers of wildlife in the wild. So a sample would be taken from the wild and then marked in some way and then released back into the wild, and then later another sample is taken and we measure the number of marked members in that sample, and that we can actually use to estimate the population size. um, Now this one has it sometimes it's the only feasible way of doing things because you can't really like test every single wild animal in the wild. I mean, could you even find them all? But if you could, it'd be somewhat expensive and time consuming, not to mention very invasive to, affect the entire population. Um, but the downsides of it is that we're making many assumptions that might not be true. So when we release the sample back in to the population, we're assuming that they're going to mix randomly, but they might not. Like wild animals often have like families and communities like, people do. We're assuming that the population size is constant, which it often won't be. Certainly, if it's over a longer period of time, you're going to have new animals born. You're going to have some animals die, and so that's going to affect things. We're assuming that the marking is durable, that it's not going to wear off at some point or come off. And we're also assuming that it's not affecting the behavior. So when you capture an animal and you've marked them in some way, so you can then track them, that could influence their behavior, in which case it could then affect the thing that you're trying to test. So there's all these assumptions we're making that might not necessarily be true. And so it's one of those things, we're getting a very rough estimate here. And so here's an example of doing that. Say if we capture 50 deer from a forest and we're giving them ear tags and then we release them again. And a few months later, we capture another 50 deer and we find that 5 of them are tags. So assuming that 50 deer is representative of the population, the fact that 10% of them are tagged, that would represent that that would imply that the first 50 that we captured and we tagged them all, that would imply that that is 10% of the full population. So we could use this to then infer that there is 500 deer in that forest. Um, so that's like a rough way we could estimate 500 deer without having to like actually capture all 500 deer. Um, so there we go. Let's take a look now at bias. So we took a look at sampling. Now we can take a look at bias and how our methods of sampling and questioning um, could lead to bias. So bias is an error that leads to the data not being representative of the true characteristics of the population that we're trying to study. So something, well, I'm going to go through some common biases, but there are many different types of biases. Like there are many different types of sampling. I've just gone through some of the main ones that you would be taught and tested on in your exams. So selection bias is a very important one. So this happens when certain groups are unintentionally more likely to be selected during sampling, and so therefore they're overrepresented. So say, here's an example. So say if I wanted to collect data regarding a town's preferences on sport, and I decide to go to the local football game to question people on their preferences of sport. Well, obviously that's going to be biased, isn't it? Like the people there are going to be more likely to say football, aren't they, than any other sport. So what would be better is if you maybe went down a variety of places in the town centre, in the mall. Maybe you went, to some local community gathering or whatever, and you get a good mix of samples. Another one would be, say, survivorship bias. This happens when we only include data that survives the study or the sampling process or whatever. And so it can lead to incorrect results because we're missing data points that we might not have been aware of. So suppose we're collecting data about UK business owners and how they conduct their businesses. So we want to just study how businesses in general are conducted in the UK. An example of survivorship bias would be maybe if we remove data of businesses that failed or closed down or whatever during the study, because maybe okay we couldn't actually get a full set of data on that business, so we thought, oh okay, we delete that data and we just stick to the ones where we have a full set of data. That would be a survivorship bias because we're now not studying businesses in the UK in general, are we? We're only studying the ones that are successful over that time window. We're not looking at what are that maybe the practices of the ones that don't work out so well. So that's an example of survivorship bias. We've got questionnaire bias, which is then okay, like we're seeing with questionnaires already, but how do we ask our questions? We so with us, and when we're trying to study a thing, we want to be completely passive observers. We want to just observe a thing and we don't want to influence it, but often we are going to influence it in some way, and we want to minimize that as much as possible. Because if we don't want out to be measuring our own influences, we want to get an objective view of what that thing is, an objective view of what's actually going on. So here's an example. Like, say if we was here conducting a study about people's opinions on recycling, and on the questionnaire I asked, "Oh, don't you think that recycling is important?" You see, like the way I phrase that question, it's almost like I'm saying, I'm assuming that it is important, and maybe you do think it's important, but you don't want to influence your sample. You want to get people's objective viewpoint on what they think. So you'd want to ask something more neutral, like, "What is your opinion on recycling?" So you're more likely to get people's actual opinion. Let's look at what should be, yeah, one last example, response bias, um, which is when you attempt to collect data from a large variety of people, but sometimes only certain subgroups of your population might respond, and you need to be aware of that. Like uh, one example would be, say, if you wanted to find how much the average person gives to charity. So, well, first of all, it's kind of like an example of questionnaire bias again, because depending on how you phrase it, you might unduly pressure people into giving a more desirable answer because they feel, oh, I should say that I give a lot more charity, so they might overstate how much they actually give. But there's also like a response bias, because if you give out this questionnaire to a whole bunch of people, people who don't really give to charity might not be very inclined to respond at all because they don't want to say they don't give to charity. There can be like that social pressure that they should be giving to charity, say. Whereas those who give a lot to charity might be keen to give their response. Or at the very least, they're very comfortable in giving their response. And so there's things like that we might want to be aware of. And so things like anonymity or whatever can be a good example there, where people can give their response anonymously. No one would like know who it is or whatever. So things like that. These are all things we've got to be aware of. Uh, so bias in general is just anything that could potentially influence your results, and you want to try and mitigate that, as reduce it as much as you possibly can in the way you sample, in the way you question, whatever. So let's look at types of data. So what kind of things would we want to detect, want to collect data on? Um, so data, uh, first of all, we can look at primary and secondary data. What does that mean? So this is about, who collects the data, how it's obtained and by whom. So primary data is when you might collect data yourself, or maybe you paid someone to collect it for your specific purpose. And the advantage of that is that you have control over the data collection. You make sure it's relevant, up to date, accurate, and unbiased. But the disadvantage is that it's expensive, it's time consuming, to do it yourself or to hire people to do it for you. And the scope of your study might then be limited because you might not be able to collect as much data. And so with less data, your results will be less accurate. Secondary data is when we have someone else maybe has collected it, like in the past, and we just can go to some online database and collect that data and use it. Problem is with that, oh no, the advantage is, sorry, is that it will take far less time because we can just go and get that data, and there might be a lot of it as well, which is great. The disadvantage is that it might not be so relevant to what we're trying to study. It might be a bit out of date, and you can't really ensure that it's accurate or unbiased. Maybe they were a little bit more loose with how they collected that data. So those are the pros and cons of primary and secondary data. We've also got qualitative and quantitative data. So this is the type of data we're collecting. Is it descriptive or is it more numerical? So qualitative data is descriptive. It captures the qualities that are being studied, whereas quantitative is numerical. So it's the quantities that is being studied. And so we can take an example here of like a house, and quantitative data, sorry, would be things like this. So numerical amounts, how many rooms, how much space there is, uh, what it's sold for, how close the nearest school is, all specific numerical amounts. Um, Qualitative data is then things like this. Like it's got hardwood floors, it's a family-friendly environment, it's a modern build. It describes the house. But so that's like an example of differences between qualitative and quantitative. And note that there are some things, like say the energy efficiency there. It could go either way. It could be quantitative or qualitative. Like if I wanted an actual numerical amount of how much energy per month it takes to run this house or something, that would then be a numerical amount or quantitative data. Whereas you have something like this, where qualitative data, where I've just said it's excellent based on some kind of criteria. And so when you're collecting data on something, you might want to decide how specific do you need to be? Do you need a specific numerical amount? Or do you need more just like a qualitative judgment on it? Like, is it excellent? Is it good? Is it mediocre? Is it bad? Is it really bad? Like something like that. So let's look discrete and continuous data. So what do these work? So today there's like a lot of words, a lot of definitions, a lot of descriptions. We're not actually doing too much math. It's actually just a lot of describing things, which we need for statistics. So when we have quantitative data, so numerical data, we can describe it as discrete or continuous. Um, so this depends on like what this determines is what kind of values can they take. Is there like an infinite number of values, or is it more like a specific sequence of values? So discrete data can only take on like countable values, like integers. And they're said to be countable because it's like a sequence. There's an order. It can be one, or it can be two, or it can be three. Maybe you're rating something out of 10, and you can just pick one value, one integer value, and nothing in between. I mean, but then it could also be decimal values like this, but maybe if it has to be 1.0, 1.1, 1.2, and nothing in between, it has to be one of those values. That's discrete value, where it's like dot, 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 like this value or this value or this value. Continuous is more like a continuous spectrum of values where you can take on any value in the range and they're not countable. There's not like an order because any two values you pick, no matter how close they are, there's always another value in between it. So say the numbers, if it's a number between 1 and 10, it could take on these numbers, 1 to 10, but it could also take on any other number that you could think of between 1 and 10. So that's an example of continuous data. Um, so you could think of it as like discrete data being like dots. It's like this point or this point or this point or this point. Continuous data is like a continuous line, and any point along that line. And you can imagine taking a window like this, and if I shrunk it down sufficiently small, there'd eventually come a point where it's like almost in between two discrete data points, and there'd be nothing in between. But the continuous line, there's always gonna be some data point in that range. So that's discrete continuous data. Examples of discrete would be like something that takes on integer values, like say like a number of people, for example, if that was the data it was collecting. Whereas continuous could be something like a time amount, like say if you're counting on a stopwatch, if someone the time someone takes, that theoretically could be as accurate as you want it to be. So let's look at types of average now. So this is when we're actually trying to analyze data. So say we've done our questionnaire, we've sampled some population, we've ensured that we haven't got bias and things like that. We've collected our numerical data, and now we're trying to uh, do some averages with it. And an average is like it represents a sort of central or more typical value of the whole data set. Um, so the benefit of an average is that it condenses even a very large data set into just a single representative value that's easy to compare within other data sets, which can help aid decisions. Like if we're trying to, what is the average of this? What is the average of that? We can compare the two quite easily. However, it's only one representative value. It doesn't measure like the spread of data, like the distribution. Like we'll talk more about that in a sec. Um, So we have a few different types of average here. We've got mode, median, and then mean. There's a few different types of mean, but arithmetic mean is the main one we deal with. So let's quickly look at what mode is. It's simply the most common value in the data set. So it's generally most useful for, say qualitative data where you might get a lot of repeat data points, with numerical values, certainly continuous numerical values. You're not really going to get so many repeat values. It's going to be more unique values each time. Advantages is that it's easy to find, easy to understand. It works for both data types, and it's not really affected by extreme values, which we refer to as outliers. The disadvantage is that it doesn't always exist. Like say if there is no duplicate values, then there is no most common value. Um, and it doesn't always use all the values of the data set. So it's not really representative as other averages. So say if we had this, which was like, say, the ages of students in like a youth group, we can spot that the most common value there is 14. There's like, well, 1, 2, 3, 4, 5, 6, 7, 8 um, people who are 14, more than anyone else. So that would be the mode. So the median is essentially the middle value of the data set. So this takes a little bit more work to calculate. Well, would not really calculate, but to more identify. Um, so it's useful for data sets that contain outliers because it only really focuses on the middle point of the distribution. And so one odd outlier, like a really extreme value, is not going to affect it much. Um, so yeah, it's not affected so much by those outliers. And it can also not just outliers, but also skewed data. This is when data is maybe leans one way or the other. Um, so rather than being like an even spread, maybe there's a lot more down this end or a lot more up this end. Not necessarily because it's biased, but maybe that is just genuinely what the data looks like. The disadvantage is like the mode, it ignores most of the data points, only focusing on the middle, and so therefore uh, it's not so representative of the data set as a whole, and it's not so good for small data sets. As you start adding more data, like the median could then jump around a lot, so it's a bit unstable. So here's an example of like, say the students in that youth group, we then log their heights in centimeters. If we want to then identify the median, which is the middle value, first of all, we have to put them in order. So you see here, I've put them in height order. And then what you do is you can read in from both sides, say, 1, 2, 3, 4, until you reach the middle. Um, or you could count out how many there are, and you can always work out what the middle is. Like if there's an odd number of data points, there will be a specific middle value. Like in this case, where it's 169. Say if I put in one more data point, like 181, one more person joins the group. Say now there's an even number and you'll find the when as you count from one end to the next, you'll get to two values in the middle. And if that happens, you've got to take the midpoint of those two values, and that will be the median right there. Uh, and one more thing to know, once you've got it ordered like this, you can easily calculate something known as the range, which is the difference between the highest value and the smallest value. So that's a handy thing to work out once we've got it ordered. Um, and yeah, ranges gives us a useful metric of like measuring our data as well. So let's look at mean. First of all, the arithmetic mean, which is simply the sum of all values divided by the number of values we have in our data set. It's commonly used average to produce a typical value for the data set that incorporates all the values. So because we're like summing up all the values are being included, which is both good and bad. Like it's good because it's representative of the data as a whole, but if there are any outliers, like the odd extreme values, like which may be incorrect values, they're getting included in the average, which might not be desirable. Certainly, if they're very extreme, it might actually pull the average a bit. Um, but it's still relatively easy to calculate. The disadvantage is that, yeah, because of the outliers, it also might not represent skewed data very well. So that if um, the mean is more affected by the skew than median is. So say if we have something like this, maybe this is the profit that a small company makes per month for 12 months of the year. So you see for each of the quarters there, 3 months each. If we wanted to calculate the mean, what we'd have to do, the arithmetic mean, is we add all this up. So, and the total of all those values comes to this, and then we divide by the total number of data points, where it's 12 here, 12 months in a year. And we'll get the average amount to be this. So this is like what the person made on average. So sometimes it was more, sometimes it was less, but this is like a representative value. Geometric mean. So this is something you're not so likely to come across, but I just want to cover it quick to make sure. So it's similar to arithmetic mean, but rather than adding them all up and then dividing them by how many there are, you multiply them all up and then take the root of how many there are. And this is typically for good for anything where we're talking about, like, say, interest rates and things like that, things that are like multiplicative, um, like things to do with scales and scale factors and all that. The advantage is that it handles those types of data better, and it's less sensitive to outliers. It can absorb those outliers much easier. Um, the disadvantage is that it's more complicated to calculate, and it can't handle negative or zero values. So depending on what you're doing, it might just not be feasible. So say if you had something like this, which was like the percentage increase on some investment from year on year. So you see the first one is like a 5% increase, then a 2%, then a 1%, 3%, so on. 0.98 is then a 2% decrease, so on and so forth. Like we've seen this before. So say if we've tracked this for many years and we want to see what was it on average. Well, what we do is we multiply all these values together. And when you do, you get this. And then we want to root it by the number of values. So here we have 13 data points. So we want to take the 13th root, which might sound, kind of strange. So uh, you might want to, just check on your calculator if you know how to do that, how to take the nth root of something. Maybe you're only familiar with square roots or cube roots. You might want to, look up how you would do that on your calculator. And when you do, you find out it comes out to this. So on average, it went up by 1.5%. We can see there. So and that would be more accurate, a more representative answer than say if we did the arithmetic mean, because interest, these are scale factors, aren't they? We're scaling by these amounts, not adding it or anything. So let's look at weighted mean, which is something you're more likely to encounter than geometric mean, which is the same thing as like an arithmetic mean, but we weigh each of the value. And what does that mean? It's basically where we're taking into account the importance um, of each data point, and so they might contribute differently to the whole, as opposed to just averaging them all, like adding them all up and then dividing out how many there are. That's assuming all points are equally important. So the advantages of weighted mean is they can take into account that relative importance and varying contributions. But the disadvantage is it's dependent on the weights being assigned correctly. So, say there might be some cases when the weights are kind of more like an estimate, and if the weights aren't quite accurate, then the mean won't be so accurate. Um, so if we look at a case like this, say if someone who's uh, finished their course in, some subject, and they got a test score of 80. The midterm result they got 56, and then they got four courseworks here that they did, and they got various scores, and the um, relative proportions of each of these are as follows. So they're not all equally valid. Like the test is contributes the most. The midterm then contributes a significant amount, and in each of the courseworks, it's just a very small amount. So if we wanted to work out what the weighted average is based on these relative importance, we would have to take that proportion of each of these values. So 50% of 80 is 40, 30% of 56 is 16.8, and then we do 5% of each of those courseworks and then add all those up. And that will get us the average score. And this is how like a lot of say certainly at like university and that your score is calculated like this. So lots all your work can count towards your end result, but not equally. So you see here on this weighted average, they get 71.4. So it'd be a different result if we weighted this differently. So you see there, we once we sum all that up, we don't have to then divide by six or anything because there's 6 data points. That's already been accounted for here by doing that weighting. Because say if we weren't doing this weighting, say if we was just doing a regular arithmetic average, um, arithmetic mean, we just add them all up and divide by six. Well, that'd be the same thing as times in each of them by six, dividing by six each first, and then adding them up. So doing these proportions like this first, and then add them up is like the same thing as that. Like that division has kind of already been accounted for, um, and but we have to do it this way in the weighted average because they're not all being divided by the same amount. So we're not taking the same proportion. So that's how we do a weighted average. So let's look at quartiles. So this is the last thing we need to look at. We've looked at averages, which are like values that are representative of the overall group, and they've got various advantages and disadvantages. Now look at quartiles, which is more like the distribution. So the average is kind of like the midpoint, but how is then the data spread around that midpoint? Is it kind of more above it? Is it more below it? Is it nicely evenly spread around it? Is it really widely spread, or is it quite narrow, like quite close to the average value? Quartiles help us understand that spread. So we've already calculated one of them. Like the median is actually a type of quartile. It's what's known as the second quartile, and it marks the 50% point in the data. So the midpoint. Then we also have the lower quartile, Q1, which represents like the 25% point, and then the Q3 represents the like 75% point. And so we can find out what that is. Like if we go back to that data set we had before and we calculated the median to be this. So here was the midpoint between those two values. Um, Now we could draw a line there, and now we look at all the data, either side, but not including the median. That's important. Here we don't include the median because it's not actually part of the data set, like 170. But say if it was 169 was the median, then you wouldn't include 169. So that's important. We look at specifically below the median and then specifically above the median. And we essentially kind of do the median again, find the midpoint, which here, the midpoint of that lower half is going to then be the lower quartile, and the midpoint of the upper half is going to be the upper quartile. And so we get 163 and 175. So now let's start like bringing all our averages together here. So here's our data set. We've got our median was 170. We've got our lower quartile was 163. The upper quartile was 175. We can then calculate something known as the interquartile range. So we saw the range before, which was the difference between the lowest value and the biggest value. The interquartile range is basically that range between the two quartiles. So we do find the distance between the lower and upper quartile, which is 12. And then we can do some, the one use of the interquartile range is to kind of estimate outliers. So the kind of cutoff point for when we consider something an outlier is like 1.5 times the interquartile range less than the lower quartile or above the upper quartile. And so we can calculate what those are here, and we get 145 and 193 by doing 1.5 times 12, which is 18. Take that away from 163, add it to 175, and that kind of gives us a range of where our data should be. Now, this is not a hard and fast rule. It's more like a rough guide. So anything outside that range would be considered an outlier. And we can see we've got one here that is very low. So that is one we would consider an outlier in this group. So based on that information, especially because it's quite far out of that range as well. We could also calculate the mean. You might want to pause here and do that for yourself. You can sort of check that the mean the arithmetic mean by adding them all up and dividing by how many there are. So whenever you have a question in an exam saying it might say calculate the mean, they're typically talking about the arithmetic mean. Um, and how where these look in terms of on like a number line, like say if we had like for simplicity, I'm just taking say 7 data points here on a number line. The median will be this one, won't it? The one in the middle. And if it's perfectly symmetric like this, the mean will also be right in the middle. It will be the same value. But if we had data, maybe it was skewed to the left. So you might have data down there. You see how it pulls the mean down, but the median is going to stay the same. The median will still be just that middle value. So that's important. And you can see how the mean is affected. Or if it's skewed the other way, you see the mean gets pushed up a bit. Um, so so you can kind of see the relationship between the median and mean. Those are the ones we tend to be more interested in. Like the mode is not so useful here, although you might want to try and calculate the mode on this data set if you'd like. So there we go. There are our types of averages and our quartiles and what they're used for on various data sets. So hopefully that's all making sense. So it's a good introduction to stats there. Um, Let me leave you with this. Did you know there's lots of interesting examples of statistics used in the real world? Here's one famous example that actually saved the lives of many men, like back in World War II. Famous man known as Abraham Wald. He was tasked with determining how to reinforce planes during World War II to protect pilots. And he made the following picture where he was tracking where planes were getting hit, like the ones that were coming back. Um, and people were then reinforcing the planes where they're getting hit because they're like, oh, okay, this is where they're getting hit. We should um, reinforce those areas. But he uh, cleverly pointed out that this is an example of survivorship bias. Like we're only seeing the planes that are making it back, but the ones that aren't making it back are clearly getting shot in places where they couldn't afford to be hit. So he said, no, don't reinforce these red areas. Reinforce the areas that of the planes that are coming back that don't get hit. And so those are clearly the areas that are important that the plane cannot afford to get hit in and still make it home. And that's what they did. And they found the survival rate of was going way up. Um, and so it saved many men's lives in World War II. So that's a great example there of stats being used in the real world and being aware of biases and how it can like lead us down the completely wrong path. So here you go. Here's our takeaways for today's lesson. So we've got 3 lessons in total on statistics. So our second lesson next time, we're going to be looking at how we represent data with graphs and charts and things like that. This is normally one of the main things we want to do because it gives us like a good, just general picture of what's going on. So I will see you there next time to look over representation of data.